Hey fellow nerds, let us continue our discussion on Opamp applications. Today we will cover log amplifier and anti-log amplifier. Let us start with the log amplifier. For that we will first take a generic inverting amplifier. For Z1 we will use a resistor and for Z2 we will use a bipolar junction transistor. The circuit will look like this. Let's take a look at this transistor. Its base is grounded. Its collector goes to the inverting terminal. But we know the op-amp will make sure that virtual ground condition is satisfied, which means potential at this point will be the potential at this point, which is 0. So technically, the base and collector of this transistor have 0 potential. We could say they are connected. A transistor whose base and collector are connected is called a diode connector transistor. And what is the significance of that? It will always be in active mode. Now, let us take the current flowing through the resistor R to be I1 and the collector current of the transistor I2. If we apply Kirchhoff's current law at the node X, obviously I1 will be equal to I2 because no current can flow into the input terminal. What is I1? I1 is the current through R. R has a potential V in here and 0 here. So I1 will be V in minus 0 divided by R or V in by R. And I2 is the collector current IC. So that gives us V in by R is equal to IC. We have a transistor over here. We know the base emitter voltage of a transistor is given by Vt log of IC by Is. Vt is the thermal voltage, 26 millivolt. IC is the collector current. Is the saturation current. In this case, IC is equal to V in by R. So we can modify the equation like this. Now, base of the transistor is here. Emitter is here. VBE is the potential between this point and this point. Now, let us apply Kirchhoff's voltage law in this loop. There is V out here. As we go on, there is VBE and then it goes to ground, which is 0. That means sum of these two voltages must be 0. Someone might think we have V out over here. As we go on, we see the negative of VBE first and then there is ground, which is 0. So V out minus VBE is 0. This thought couldn't be more wrong. Let me show you a tip that will be very useful while applying KVL, especially when the loop is not very much visible. Because first of all, do you see a loop over here? No, right? Well, let me show you the loop. For that, I will visualize V out using a cell like this. So we have a potential V out over here. I can show it using a cell like this. A cell of potential V out. So here we have ground. Here also we have ground, which means this is a loop. Now using this visualization, let us apply KVL. V out goes from negative to positive. As we go on, VBE is also from negative to positive. And then we go to the ground. So the relation is V out plus VBE is 0. If V out plus VBE is 0, that means V out is equal to negative of VBE. We already have an expression for VBE. So V out is negative Vt log of V in divided by R Is. Is is the saturation current, it is a constant. R is the resistance of the resistor we give over here. We have control over it. RIS is the product of a resistance and a current, so it is a voltage. We can actually call this the reference voltage with respect to which we can obtain our output. Then the equation will look like this. Clearly, output is proportional to log of the input. What we have is a logarithmic amplifier. Let us now answer some questions based on what we learned. The first question is, why is the output negative? You can see the output as negative of Vt log of V in by V reference. Why is there a negative? Imagine the input increases. Obviously, when input increases, current through the resistor will increase. But this is the same current that flows into the collector of our transistor. That means when V in increases, collector current is increasing. But collector current of a transistor is controlled by its base emitter voltage. So if IC has to increase, that means VBE is also increasing. That means if IC has to increase, VBE has to increase. Now VBE is VB minus VE. Base is at the ground. So VB is always 0. That means VBE is 0 minus VE or simply negative of VE. But we want VBE to increase. That means negative VE should increase. The only way that will happen is if VE becomes more negative. So we can conclude, since VB is 0, for VBE to increase, VE should become less than 0. Now the emitter is directly connected to the output. That means Vout is equal to the emitter voltage. If VE should become less than 0 for the whole circuit to work, then Vout is also going to be less than 0 or negative. This explains why the output is negative. Now, we took the direction of current through R like this. R has a potential V in here and Vx here. But Vx is 0. That means for the current to flow in this direction, V in should be higher than 0. Technically, we assumed V in is positive. The next question I want to answer is, what if the input is negative? Will it still work? We can answer this question in two ways. The first one is very easy. All you have to do is look at this equation. Output is negative Vt log of V in by V reference. V reference, as we know, is R, Is. R is a positive value, Is is a positive value. So if input is negative, that means we are taking logarithm of a negative value, which is mathematically not possible. That is the first way of answering this question. Mathematically, this is not possible. But as an electronics engineer, we should be able to explain why the circuit won't work, not just the math. So let us figure out the physical reason why this won't work. If Vin is negative, the first thing that changes is the direction of the current. We have zero potential here. If Vin is negative, then current has to flow from the higher potential to the lower potential like this. Current through R will be negative. But where is the current coming from? Obviously from the collector of our transistor, like this. But is that possible? If current has to flow in this direction, that means it has to come from the emitter to the collector, which is not possible. So if input is negative, no current will flow through it. Technically, the connection between output and the point X will be lost. That means the feedback is lost. So the negative input you give over here will reach the inverting input terminal. The Opamp effectively has an infinite gain now. So output will be at positive saturation voltage. This is why the circuit won't work. Now, what if your input is negative and you want to work with it? Either we can use an inverter and make it positive, or use a PNP transistor instead of an NPN one, because then the current will be able to flow in the opposite direction. Now, we already saw that the collector and base of the transistor are grounded. They are both at zero potential. That means the collector and base are technically connected. We are only using the base emitter junction in the circuit. And the base emitter junction is technically just a PN junction. The transistor technically is working as a diode. Then why don't we use an actual diode instead of this? Why can't we have the circuit like this? Even the current voltage relation will be the same. Current through a diode is given by saturation voltage E to the power Vd divided by Vt. Everything will be the same, and you will see that output is proportional to log of the input. But still we prefer a transistor over a diode. The first reason is this. For a practical circuit, current voltage relation contains the ideality factor eta. ID is Is e to the power V in by eta Vt. For a transistor, the value of eta is approximately 1, and that makes a practical circuit closer to being ideal. Along with this, a transistor also has a wider dynamic range. It is the range between the smallest signal it can handle and the largest signal it can handle without distorting or saturating. Dynamic range for a transistor is much better than that of a diode. Along with this, a transistor also provides better temperature stability and consistency. That is why a designer would prefer a transistor over a diode. The next question is, why take log of signals? What is the practical use of taking logarithm of a signal? For that, let us take this graph. On the y-axis, we have log of the values on the x-axis. We can see that In the low amplitude region, curve is very steep. That means a small change in the input causes a comparably large change on the log axis. As the amplitude increases, the curve gets less steep. Here, even a larger change in the input will only produce a small change on the log axis. So on the log axis, small inputs expand and the large inputs compress. We can say that a log function makes smaller changes bigger and bigger changes smaller. In more technical terms, it amplifies weak signals and attenuates strong signals. But then again, why is this useful? Let me visualize to you a use of taking log of a signal. For that, I need a signal. This is what I'm taking. You can see how wild this signal is. It goes everywhere. It's difficult for us to learn, analyze, or compare signals like this. They are so wild that you can't see the complete picture at the same time. Let's see how this will look like if you take the log of it. This helps you see the full picture. Taking log of a wild signal is like taming it. Once the signals are calm, you can compare, measure, or analyze them without any chaos. This is one use of taking log of a signal. Another one is, if the input shoots up too high, the circuits may saturate. But if you tame the signals by taking log of them, we can still work with them. Also, nature is exponential. What I mean is, physical quantities like light intensity, sound, chemical concentration, etc. change over order of magnitude. They do not change linearly. So if we are trying to sense them and measure them or compare them, it will be very difficult because these signals are going to be wild. So we tame them before working on them. Taking log of signals also makes math inside the circuits easier. For example, let us say we have to display the product of two signals x and y. All you have to do is take log of x and log of y and add them, because log of x plus log of y is log of xy. Multiplication can be done simply through addition. The same way, if you want x by y, again take log of x and log of y, subtract one from the other. Log x minus log y is log of x divided by y. Division becomes subtraction. Assume we have a wild signal that looks like this. It has large changes as well as small changes. We want to compress it. Let us see what happens if we apply linear compression. That means the entire signal will be compressed equally. The output will look something like this. The information from the larger changes are retained, but what happened to the smaller ones? There is a chance that this part of the signal may be lost in compression. If we use logarithmic signal compression, this is how the output will look like. Bigger changes have become smaller, but the smaller changes are almost the same size. When you pass a signal through a logarithmic circuit, the small amplitudes stay almost the same, but the large amplitudes shrink a lot. That's because logarithm doesn't look at how much the signal has increased. It looks at how many times it has increased. A tiny change at low levels is a big deal, so it keeps it. But the huge change at high levels will be compressed into a small step. In simple words, we can say small changes are compressed less than larger changes. So high amplitude portions of the signal are compressed more than the low amplitude signals. Let's now analyze a logarithmic amplifier that is made using a practical op-amp, which means open loop gain of the op-amp is finite. Here the primary difference is that virtual ground concept will not be perfectly followed. We cannot say Vx is equal to 0. Since Vx is the potential we give at the inverting input terminal, we can say Vout will be negative AO multiplied by Vx. That means Vx is negative Vout divided by AO. Here again, base and collector of the transistor are at zero potential, which means they are basically connected. Transistor is diode connected, which means it will always be in active mode. Let us apply KCL at point X. There are two currents, I1 and I2, and they will be equal. I1 is the current through R. R has a potential V in over here, Vx over here. Remember, Vx is not 0 this time. So I1 will be V in minus Vx divided by R. I2 is the collector current and this should be equal to that. Now, base emitter voltage is given by Vt log of Ic by Is. Ic is this much. That gives us this. Again, we can say V out is negative of VBE. Then V out will be negative of Vt log of V in minus Vx divided by Ris. Here also we can call Ris the reference voltage. Then the final output will be this. Let us now move on to anti-logarithmic amplifier. Again we have a generic inverting amplifier. This time we'll replace Z2 with a resistor and Z1 with a transistor. Like this. Wait, I haven't added the transistor. That's because I'm a little bit confused as in how to connect it. For example, let me take an NPN transistor and connect it like this. Let us assume we are taking positive input this time also, because obviously you cannot work with both positive and negative inputs in the same circuit. We have positive V in, we have 0 Vx. That means current should flow in this direction, and obviously transistor is okay with it. But there is one fundamental problem. For the transistor to be always in active mode, it should be diode connected, which means base and collector should be shorted. Base and collector should be at the same potential. But here base is at 0. Obviously this is not a diode connected transistor, so it will not be always in active mode. What if I connect the emitter over here and collector over here so that collector will be at Vx, which is 0? Let us try that. Now collector is at 0 potential, base is also at 0 potential, transistor is diode connected, it will always be in active mode, but current will not be able to flow in this direction. We started assuming V in is positive. Vx obviously is 0. Current has to flow in this direction, but this transistor will not allow that. What I'm trying to tell you is, we cannot use an NPN transistor. We'll have to use a PNP transistor if we want to work with a positive input signal. So let us replace this with a PNP transistor. Now collector is at 0 potential, base is at 0 potential, and current can flow in this direction. Let's mark the emitter current here. Here we'll have the collector current, and the current through the resistor can be called IR. Let us also mark VEB. E will be at positive potential and B will be at negative potential because this is a PNP transistor. Now, if we apply Kirchhoff's voltage law in this loop, we should get V in is equal to VEB. Or is V in equal to negative of VEB? We had this confusion before also. What did we do? We replaced the potential with a cell of the same potential. So here I will replace V in with a cell of potential V in. Now even the loop is clearly visible. It starts from a ground and it goes back to ground. Clearly a loop. If I replace V in with a cell of potential V in, I can see V in is going from negative to positive. As I go on, VEB is from positive to negative. So for KVL, I have to write V in minus VEB is 0. That means V in is equal to VEB. Now, for a transistor, emitter current is almost equal to collector current. Here the collector current will be equal to the resistor current. So we can write IR is equal to IC, and they are approximately IE itself. IC is the collector current. It is given by IS e to the power VEB by VT. VEB because we have a PNP transistor. But VEB is V in. So we can write IR is IS e to the power V in by VT. But IR is the current through the resistance R, who has a 0 potential here, V out potential there. So the current is 0 minus V out divided by R, which is negative of V out by R. Equating these two expressions, we can write V out as negative ISR e to the power V in by VT. IS multiplied by R can again be called reference voltage. That gives us our final expression. Clearly, output is proportional to e to the power of input. We have an anti-logarithmic amplifier. Obviously, this circuit can be used to recover the original signal from a log amplifier. Let me show you an instance where we can use this. Assume that we want to display the product of two signals x and y. First, we'll pass x and y through log amplifiers. So we get log x and log y. Then we give these as an input to a summer. We will get log x plus log y, which is the same as log of xy. Now, if this passes through an anti-logarithmic amplifier, we get e to the power log of xy, which is xy, the product of x and y. The same way we can show division also. Take x and y, pass them through log amplifiers, we get log x and log y, give them as inputs to a subtractor, we get log x minus log y, which is the same as log of x divided by y. If this passes through an anti-logarithmic amplifier, we get e to the power of log of x by y, which is x divided by y. So that's all about it for today. See you in the next video. And please don't forget to subscribe.